Okay, so I welcome you all and I thank you all to be present in the class right now. And today we'll be talking about the quasi-classical case. And before we go into the concept of the quasi-classical case, I would like to start an example. I would like to reach out to this argument that what quasi-classical case means in quantum mechanics. I would like to take the help of an example. Now, the example is like that. Let us assume that that you are standing on a cliff, on a mountain cliff. Okay, this mountain is somewhere in the ocean. You are standing on that cliff, and far across in the ocean there is a ship, and this ship has flashes of light coming out of it. You are on the cliff and you are looking far in the ocean, and what you see is the flashes of light. And the moment you see the flashes of light, you realize that there is something, because the rest of the ocean there is no light, but the direction in which you see the flash of the light, you predict something about it. You predict that there is something. And this something, where from this light is coming, you are calculating it. By calculating it, you are predicting that there is something far in the ocean. Not only this thing, you can also calculate the motion. You can predict in which motion that ship is going. You have a ship, it's emitting the flashes of light. You are on the cliff. You are looking at the ship. You are looking at the light. You are analyzing the light from the cliff. In the framework of classical physics, you can exactly predict, you can exactly talk about it, how fast this ship is moving. You can calculate it merely by the light that's reaching us from that ship. Are you getting my point? Now imagine you have the same problem, the flashes of light, but this problem you are working out at very, very small scale. You have the same ship at the small scale. The same ship at the small scale means an atom, a molecule. And you are trying to analyze the same problem from the cliff. But now the scale at which you are observing the events that are happening in the ocean is very, very small. Now, when you observe, you find very strange things. Your calculations tell you that the ship is present at two places at the same point of time. Now you are again observing the same problem. You see that the ship doesn't appear at all. The same problem, you see, you make the calculation, you find the ship is at three places at the same time. You are working on this experiment from the same cliff. What are you doing now? First, when it was a big ship emitting the light, what was happening? It was completely predictable. You could predict everything about the ship. You could predict every minute action about the ship. And you could always say that there is one ship in the ocean. But when you take this problem to a very, very minute scale, what is happening? Your predictions are not clear. Your predictions are probabilistic. Sometimes you observe, you find 2 ships at the same time. Sometimes you find 3 ships. Sometimes you don't find a ship at all when you look at the ship. This is quasi-classical case. Quasi-classical case connects, it tries to connect the classical laws with the quantum laws. Getting my point? So, what you have a classically known situation, and then you are trying to connect this classical physics with the predictions of the quantum mechanics. This is what is called as quasi-classical case. It's also known as WKB approximation, because these were the 3 people who developed a theory to explain the transition, to explain the results of quantum mechanics, the results of classical mechanics from quantum mechanics. Okay? So that's the case. So what we have quasi-classical case in quantum mechanics. So you got the idea that I was trying to tell you? So you are moving from a state where things are probabilistic in nature to a state where things are completely predictable. So now let's go with this. So the quasi-classical case connects the quantum world with the classical physics, as I was telling you. I gave you the example to understand it. Okay? It shows how classical behavior emerges under certain conditions. So classical physics appears to be the approximation of quantum mechanics. What is purely predictable to us is an approximation of quantum mechanics. Classical physics, what it does, it describes definite positions, velocities, and you have trajectories of the objects, right? This is classical physics. Quantum physics, what it does, it explains the microscopic systems using probabilities, uncertainty, and wave-like properties. The ship, which was a solid object in the classical framework, it has taken a wave-like nature, where it is giving you the superposition, and you are able to find 3 ships at the same point of time. You are able to find 2 ships at the same point of time. The quasi-classical case that we are going to discuss, what it does basically, it bridges the gap. It tries to bridge classical physics with quantum physics. So the quasi-classical case acts as a bridge between these 2 views that we talked about, showing where quantum and classical descriptions can overlap. Is this clear? I think it's clear. Now, when you have quantum systems, when your quantum system becomes large, their behavior resembles the predictions of classical physics. Do you remember the Bohr's correspondence principle? That will be the target of this theory. When you talk about the microscopic systems in the framework of very large quantum numbers, large principal quantum number, it purely resembles with the classical predictions. So So this is the case. When your quantum system becomes large, their behavior resembles predictions from the classical physics. Niels Bohr, what he did, he introduced the correspondence principle. Quantum laws must agree with the classical laws at the large scales. This was his argument. And it's true. We understand it from the ordinary quantum mechanical rules, right? So what we have a connection. We have to develop a theory that connects the quantum with classical. The ship that I talked about, for me it was a particle. I could measure its dimensions. But the ship, I observed when its dimensions are comparable to the dimensions of atoms and molecules, it no way behaves like a point particle. It behaves like a wave. So particles in quantum mechanics can be seen as wave packets. It's a group of waves which under certain conditions move like a classical particle. We have also done this kind of problem where we finally calculate the group velocity. You remember that? And that group velocity comes out to be equal to the particle velocity. So that's what quasi-classical case is. In quasi-classical situations, the uncertainty is small. See, it's a bridge. In pure quantum mechanical framework, you have large uncertainties. So here you have small uncertainty and the outcomes look almost predictable. Okay? The outcomes that you have, they look almost predictable, like in classical physics. Electrons in high energy states orbit atoms in ways that appear similar to the classical planetary orbits. See, this is a very beautiful argument. You have an electron in the ground state of hydrogen atom. Its state is very, very uncertain. It has probabilities. You have the cloud of probabilities around the nucleus of hydrogen atom. But the same electron, if it goes to the higher principal quantum numbers, when you take it to the higher number, it resembles to the motion of the planets. That's what quasi-classical case is. That's how it limits. That's how the classical physics becomes an approximation of quantum physics. So here, what seems to be plausible is that quantum mechanics is more fundamental than that of classical physics. Light has quantum properties. You know it. But in everyday optics, ray of light behaves classically. An example of the quasi-classical case. Isn't it? You make use of light to explain Planck's black body radiation law, assuming that light is made of particles. And each particle has an energy equal to h nu. You use the same framework to explain the famous photoelectric effect, for which Einstein got Nobel Prize. And we make use of light in our day-to-day lives in the field of optics. We assume it as a ray, and it works. But fundamentally, light has a dual nature. So, what does it mean? It means light itself is an example of the quasi-classical case. Because when you treat the same light in a double-slit experiment, it doesn't behave like particles, right? It behaves like a wave. Now, coherence, yeah, what's the coherence? Come on. What are the coherence states? Okay. You have a basic definition of coherence depending on the situation you are talking about. say for example, in case of lasers, okay, you take the electrons to the higher energy states, then you allow it to go in a state what's called as metastable state, and what happens there? There you have stimulated emission of radiation, and that stimulated emission of radiation is possible only if the electrons that are in the metastable state, they have the coherent phase. They all have the coherent phase. So there are situations where you can say the states of light, they are coherent states. They resemble the classical electromagnetic waves in their behaviors. In classical waves, you also have coherent waves. In classical physics, we know how to superimpose two waves, right? If their initial phase is same, then how do they superimpose either constructively or destructively? At very small scales, quantum effects dominate. What was true, what was a reality for you standing on the cliff, now it is dancing. You're not sure what's going on. The light is coming from the same spot in the ocean, but the moment you observe it, you have, at every observation, you have a different result. At large scales, classical physics provides a good approximation. That approximation comes from the quantum mechanics. So the quasi-classical approach is useful in atomic physics. It becomes the backbone to understand some of the advanced courses in physics. Atomic physics, optics, chemistry, for simplifying the complex problems. It provides an intuitive way to understand how the strange world of quantum mechanics gives rise to our everyday classical world. So the quasi-classical case highlights the continuity. So it's a bridging gap between the quantum and the classical descriptions. Bridging certainty and probability, right? So this is our introduction to the quasi-classical case. So now let's go with it and let us discuss this case in general. So what we are going to discuss is the quasi-classical case. Now, before we go into the mathematical treatment, let me draw a potential. Okay? Now, this is our potential, okay? And this potential can be divided into two parts. And here I will call this point as point A. Here I will call this point as point B. And this is V of x. Okay? Now, this point A and the point B. Now what I have divided this potential into three regions. Now this is, say for example, this is region 1, this is region 2, and this is region 3. See, you are dealing with a problem in which you have a total energy. This total energy can either be less than that of the potential energy, it can be less than that of the potential, or this energy can be greater than that of the potential. Now this region 2, this is a region in which E is greater than V of x. I'm taking a one-dimensional problem. Okay? In this region, E is greater than that of V of x. And in region 1, E is less than V of x. And in region 3, again, E is less than V of x. Clear? Now, the region 2 that you see, it's okay, nothing wrong with it. The energy of the particle is greater than that of the potential. You have a potential, you have a ball, you have a ball. The energy of the ball is greater than that of this ball. Now, if the energy of the ball is greater than that of this ball, what will happen to the ball? It will cross the ball. So this region 2 is called classically allowed region. Classical physics has no objection with it. Classically allowed region. Right? Clear? Okay. Now as you move away, at the point A, I mean above the point A, because point A is something about which we have no information. The points that are above than this point A, in this case, E is less than V. This situation is true in both the regions. It's true in 1, it's true in 3. Now these regions, 1 and 3, we call these regions as classically forbidden regions. Classically forbidden region. Clear? Now what about point A and point B? At the point A, E is equal to V. At point B, E is equal to, this is the point of connection. And we cannot exactly solve it. This is the point of connection. Point A and point B, we call them turning points. We call them what? Turning points. Because your problem is moving from classically allowed region to a classically forbidden region. Are you getting my point? So point A and point B, these are abstract points. Physics has no explanation for these points. The physics can be solved only in vicinity of these points. The physics can be solved only in vicinity of these points. That's what quasi-classical case is. You solve the problem to move from classically allowed region to the classically forbidden region. Because the potential I described before you, I said you have a potential, okay? In the first case, the energy of the ball was greater than that of this potential. So there was no problem in classical physics that this ball will penetrate this potential. But now the ball has energy less than that of this potential. Are you getting my point? Do you see that you are moving from classical framework to the quantum mechanical framework? Because classical physics tells you that the particle will never cross the turning point. The particle will never cross the turning point. For the classical physics, this potential is impossible for my ball because the energy of my ball is less than that of this potential. Getting my point? So your problem is broken into the three important parts. you have a classically allowed region, you have the turning points. I'm again telling you, we know nothing about turning points. But what we do, we exploit the region close to the turning points. And what we do here, we assume that the potential is varying very slowly. Because if you want to calculate anything in physics, you want to slow. So what we do, we assume that there is a potential close to these turning points. And this potential is varying slowly. It becomes a very strong mathematical tool for us because it simplifies our equations. You will see the moment we will go into the actual framework. Clear? So you have a situation. You have a situation in quasi-classical case in which you have to describe this system. And you see turning points. The turning point is telling you no. Classical physics cannot. It cannot tell you anything about what is happening after the turning point. But using mathematical formalism, we are able to move from, this is what Landau book will explain you. If you choose that book to read comprehensively, the framework for the quasi-classical case is this thing, that how you can exploit mathematics, you can exploit Schrodinger's wave equation to move from classically allowed region to classically forbidden region. And we have the basic equation of quantum mechanics. What's that? That's Schrodinger's wave equation. Okay? So let me write down that equation. So this is the problem. You understand the problem? This is what we are going to discuss mathematically. So I can move ahead and I would like to write down the Schrodinger's equation. Now, obviously, you will be thinking about time-independent Schrodinger's equation. And what is that? Now, if I choose my eigenfunction as, say, psi of x, I can write down the Schrodinger's equation. What's that? In one dimension, that's d2 psi by dx2 plus 2m by h cross square e minus v of x of psi is equal to 0. Okay? This is our basic equation. And this equation should take us finally to Bohr's correspondence principle. That's the target. The half of the unit is all about it. Right? So, this is your starting equation. And if I think about this equation numerically, I mean, if I assume that v of x is constant, that means e minus v is what? It's a constant. So I can choose this equation as d2 psi by dx2 plus some capital K squared psi equals 0. What about K? K is a constant. Now getting the point. K is a constant. So if K is a constant, you have a differential equation and you can presume a trivial solution for this equation. And what's that solution? I can choose my solution as, say, psi is equal to e to the power of, say mx. Okay? Choosing the solution as psi is equal to mx. Take its derivative, what you will get? You will get psi dash. That will be m e to the power of mx. Now take another derivative psi double dash. And what you will get? You'll get m squared e to the power of mx. Now what is your psi double dash? It is d2 psi by dx2. Right? So we can immediately use this in our differential equation that we have. What we'll get? What we'll obtain? We will obtain m squared psi of x plus k squared psi of x equals 0. Right? And you can use this psi of x. What's that? That is m squared e to the power of mx plus k squared e to the power of mx is equal to 0. Now e to the power of mx times m squared plus k squared is equal to 0. Now this thing is not equal to 0 because we started with psi equal to e to the power of mx. So this thing is not equal to 0, that means m squared plus k squared is equal to 0. So m squared plus k squared is equal to 0. So m squared is minus k squared. So m is plus minus under root of minus k squared. So square and root will cancel. So m will be plus minus iota k. Clear? So I can think of writing the solution for this constant potential as psi of x is e to the power of plus iota kx plus e to the power of minus iota kx. I think we'll stop here, okay? And we'll proceed tomorrow. We will go deep into the mathematical arguments and we will see. If you have any questions, you can ask me. Come on. Any questions? Yes? Come on. So you don't have any questions? Come on, go with it. Okay, bye. So a very good morning to all of you. And I assume that everybody is fine. And in continuation to yesterday's discussion, we will move on because we have been talking about the quasi-classical case, which is also known as WKV approximation, right? And as I rightly said, this WKV approximation basically takes us from quantum mechanical predictions to the classical predictions. And if you rightly remember, we had a situation like this, having a potential like this, and this potential has classically allowed region and classically forbidden region. So if you rightly remember, we have a situation like this. So this region is your region 1. This is classically forbidden region. And these points, this is point number 1, this is point number 2. These are called the turning points. You cannot exploit physics at these points. But what you can do is you can exploit physics in vicinity of these turning points. And then this was your region 2, and this region 2 is classically allowed region. And finally you have the region 3, which is classically forbidden region, right? So we started with the constant potential, and and what we did, we obtained the solution to the Schrödinger's wave equation, right? So what is the idea is that we want to have more precise solutions to the Schrödinger's equation. And the idea is clear. You want your potential to be slowly varying, right? So only you can proceed in this direction when you assume that the potential is slowly varying in your problem, right? So, so what we have, if I write down a one-dimensional Schrödinger's equation, d2 psi by dx2 plus 2m by h cross square e minus v of x. Now this case we have been discussing for e is greater than v of x. And here we have an important assumption. The assumption is that the potential that you have, the potential is slowly varying. So now, if you rightly remember, yesterday I chose a capital K for 2m by h cross square e minus v of x. And that was constant because we chose constant potential. Now your potential is varying, so I would like to write down the Schrödinger's equation. So that will be d2 psi by dx2, then plus, now I'll use a small k here, okay? So k square of psi equals 0. But now you are working in a situation where e is greater than v of x. And this is your classically what? This is classically allowed region, isn't it? Classically allowed region. So what we are doing, we are solving the problem in classically allowed region, assuming that the potential is varying slowly. Now in this case, this k is a variable because you assume that the potential is slowly varying. So to choose a solution, suppose I choose a solution, say psi of x is equal to a e to the power of iota u of x. Okay, now u is a function of x. So what would I like to do? I would like to calculate its first derivative, then calculate its second derivative, and then I would like to insert that in my original differential equation that I have, the Schrödinger's equation. So let us take its derivative first. Yeah, it will be d psi of x by dx. This is going to be a iota u of x. See, u is what? U is the function. Okay? See, when you differentiate an exponential function, the exponential function does not change, but the exponent has to be differentiated. But here, u of x is the function of the x. So I have to write the derivative of iota u of x. So what will be that? That will be, that's going to be du by dx, e to the power of iota u of x. Is this clear? Right? Okay, so this is the internal derivative of the exponent of this exponential. So here, what I have calculated, the first derivative of psi with respect to x. Now, I would like to differentiate it again. So, I would like to differentiate it again with respect to x. So what you'll get d psi by dx. So this will be equal to ai will be out, Now inside you will have a UV rule, okay? So in case of UV rule, suppose the first term is the u. So the derivative of du by dx will be what? It will be d2u by dx2. And v will remain as is. That means e to the power of I u of x will remain as is. Right? Plus. Now du by dx will remain as is. Okay? Now what you will do? You will differentiate the exponential function. And you will get another du by dx by differentiating the exponent, and you will remain with your exponential function eu to the power of x. Is it fine? Yeah? Yes, yes. Iota has to be here now. I would like to multiply that iota here. That's right. Fine. Okay? So what I'll get? I'll get d2 psi by dx2. Now this is equal to iota d2u by dx2 a e to the power of iota u of x. This is our first term, and this ai will multiply to the second term. So iota will give us iota square, that will give us minus. So here you will have minus, you will have du by dx whole square. Can I write like this? And then you will have a e to the power of iota u of x. Clear? So we got the double derivative of the solution of Schrodinger's equation. But we have to go with the assumption, because it will make sense only when you will be using the boundary condition in your problem. So what you have now, you have this thing. So for this double derivative, I can use Schrodinger's equation. Okay? So what was the first term? Come on. It was iota. It was iota d2u by dx2. This is the first thing, right? Then minus a. Okay, I will not write a, minus, yeah, du by dx whole square, right? Okay, then you have plus k square, plus k square. Then this whole thing is multiplied by a e to the power of iota u of x, and this whole thing is equal to 0. Right? Now see what's happening. What's happening basically is your choice is that the potential is slowly varying. So if the potential is slowly varying, then the double derivative of this u will be equal to 0. So for slowly varying potential, yeah, for slowly varying potential, this d2u by dx2 will be equal to 0. Is this clear? Now if this is equal to 0, what you will get? You will get that this minus, yeah, minus du by dx whole square, yes, whole square, then plus k square. This is multiplied by a e to the power of iota u of x. And this is all equal to 0. Right? So all of us know that this a e to the power of iota u of x, this is not equal to 0. So what is equal to 0? It is du by dx whole square is equal to k square. Right? Okay? So now what we can do, this square we can take off, And obviously you will have to incorporate plus minus. We will do that later on. But here, what I will have du equals k dx. Right? Obviously you will have plus minus here. We can incorporate it. You can yourself incorporate it because it annoys me a lot. That's why I'll not use it. Okay? So what will I do? I will integrate it. So on integrating, I'll have integral du is plus minus integral k dx. So differential and integral will cancel. Then u of x that you have introduced is plus minus integral k dx. Right? So this is modifying our wave function, the solution to the Schrodinger's equation. What will be that? The solution to the Schrodinger's equation. Now I started with psi of x, but I will use psi 0 for it. So I'll be using psi 0 for it. So psi 0 of x will be what? E to the power plus minus iota integral k of x d of x. Now this is called zero order solution. This is called zero order solution of Schrodinger's equation, right? So what we have psi 0 of x is a e to the power of plus minus iota k of x and d of x. Now keep that in mind, this is a small k. And you are working in e greater than v of x, right? Okay, so it's fine up to this. Now let me again differentiate this psi naught of x, okay? Because I wanted to differentiate it again, that's why I chose psi naught of x, and I wanted to define it in order to tell you that this is the zero order solution of the Schrodinger's equation. So I will differentiate it again. So what will happen? You will have d psi naught of x divided by dx. Yeah, what will be that? That will be a. Are you getting? Yeah, exponential will remain exponential, but you will have the internal derivative. So what will be that? That will be iota k plus minus. I will not write plus minus, okay? You will accommodate that yourself. So then you will have e to the power of iota integral k of x d of x. Am I right? Okay? Now what should I do again? I will differentiate it again. I will differentiate it again, so I will have the double derivative. So I will differentiate it again. So what I'll have d2 psi naught by dx. Okay, what is outside? What is outside? A iota is outside. A iota is outside, and then you have d by dx of k of x. K is the function of x. Okay? And then e to the power of iota integral k of x and d of x. This is it. Okay? Right? So now we can move on from here. So ai will remain out. Now you would like to differentiate. So if I differentiate u first, what I'll get? I'll get dk by dx. V as it, that means e to the power of iota integral k of x d of x. Right? Then you will have plus. Yeah? Plus what? K as is. Come on. And the differentiation of this. The differentiation of exponential will be exponential, but you will have to take the internal derivative. So it will be multiplied by iota of k. So you will have your own exponential integral k of x and d of x. Fine? Okay? So how can I manage this now? Come on. So this is a, so iota, here you have iota, you will have this iota will multiply with this iota. Okay? What you will get? You'll get iota square. So what you will get from here? Come on. So what we'll get? Yeah. So we will have d2 psi naught by dx2. Okay? What will be that? That will be iota, yeah, dk by dx. And then you see this iota will multiply to this also. So it will become iota square. Iota square will make it negative. So it will be minus k square. It will be minus k square. And outside you will have psi naught. Right? Because psi naught is ae to the power of the same thing. Now what does this equation tell us? This gives us a condition for the problem that we have been solving. What we imagine here is that the potential is slowly varying. Its variation is close to the de Broglie wavelength. Okay? So you have de Broglie wavelength, okay? And the potential varies in such a way that it's close to the wavelength of de Broglie. So for that, what we have a condition for that. What is that condition? That condition is, okay, this is k squared, okay. The condition is that this term that we have, dk by dx, its magnitude should be very, very less than k squared. Now see, what is this k? K is not a constant, but it has a value. And that value has a link with the wavelength of the particle. You also call it wave vector in many situations. So you see, the variation of lambda, I'm defining here the variation of lambda over a very small length. And it should be very, very less than k squared. So how can I translate this into a number? I can also write down 1 by k squared dk by dx. Its magnitude is very, very less than 1. This is an important condition for the quasi-classical case, right? So we are mathematically translating our arguments into the variation of your potential should be of the order of de Broglie wavelength, right? Okay, now let's move on. Now let me define psi 1 of x. And I will define it as, say, f psi naught. F is a function of x. Psi naught is the zero order solution. And I'm using psi 1. Then you can use psi 2, you can use psi 3. As more as you will move on, your solution will be more precise. It will be more close to connect. Right? So what's going to happen here? Now what I have? Psi 1 of x. F and psi naught. What is psi naught? So psi 1 of x is, yeah, it is f, but psi naught, it is a e raised power iota u of x, but u of x is already, okay, u of x. So we got that as integral k of x and dx, because u of x we calculated, huh? Okay. Now this is it. Now you have two functions. F is the function of x, and then you have the exponential as a function. So what you will do, you will find psi 1 prime. What you will get. So A is out. Inside you will have F as its differentiation of this thing. What will be that? Iota of k e to the power of iota integral k of x d of x. Am I right? Then plus plus e to the power of iota integral k of x d of x as its and f dash of x. Am I right? Fine. So the calculations that I did in the previous case, I chose the second derivative. In the similar fashion, you will go with the second derivative. And when you will go with the second derivative, you will come up an equation. And what will be that equation? That equation will be f double dash, it's the double derivative of f, plus minus. Now I am incorporating this plus minus. Again, we would like to get it out, but I want to remind you that this plus minus is there. Then 2 iota f dash k, then plus minus iota k dash f. Psi naught equals to 0. This is the equation that you will obtain, right? This equation you will obtain. So what do you expect from this equation? You know that this psi naught is not equal to 0. What does that mean? That means the bracketed term is equal to 0. So what we have f double dash. Then we have plus minus 2i f dash k. Then you have plus minus iota k dash f. Getting the point? Is equal to 0. Again, use the same condition. What's the condition? The potential is slowly varying. And potential is the function of position. So position is slowly varying. Right? So the double derivative term will be 0. This f double dash will be equal to 0. So what you will be left with? You will be left with this part. And what is that? I will take off this plus minus. So this is 2i. Come on, you tell me. F dash k. 2i f dash k. Then plus I k dash f plus I k dash f is equal to 0. Right? So the dash you understand. The dash gives you what? It gives the derivative with respect to the x. So I can write down 2i. For f dash, I will write k is here. I will write df by dx. Okay? This will go on the other side. This will become minus. Okay? So iota will be there. And k dash. F I will write as its. For k dash, it is dk by dx. Did you remember when I first differentiated it? I forgot to write down the internal derivative of k of x. There, I think I committed a mistake. I wrote only k of x. It has to be k dash of x. Okay? So you will correct that thing yourself. So you can remove this dx and dx. You can remove iota and iota. So what you will get df. Bring that f here. df by f is equal to minus 1 by 2 dk by k. right? I got this k down, I got this f down. So what I have, df by f equals minus 1 by 2 dk by k. Now, the equation is demanding integration now, right? It's demanding the integration. So you integrate it. So what you will get log of f is equal to minus 1 by 2 log of k, right? But all of you know that n log m is log m raised to power n. So I can take this minus 1 by 2 on the other side. So this is log of f equals log k raised power minus 1 by 2. Right? Let me keep minus there, otherwise it will cause me the problem. Let me put the minus here. Okay? I put my minus back, so this will be k raised power 1 by, because I want to bring it back. This is indefinite integration, so you will have to introduce a constant. Are you getting? So what I'll get here, this is log f, this will come in this direction, this is log k is equal to log of k under root of k basically, is equal to a constant. Now this is log m plus log m, so this will be log f under root of k is equal to constant. Okay, now we can take this log on the other side and it will work with a constant, you will get another constant. So what you will have f under root of k is equal to constant. Say that constant is, say let me call it constant. So what is f? F is constant by under root of k. Isn't it? Isn't it? You saw the solution that I chose. What was that? That was psi 1 is equal to f. But for f, what I will write? I will write constant divided by under root of k. This is k of x. K, it's the magnitude of k of x. Right? Then you have psi naught. What was that? That was a e to the power of iota integral k of x d of x. Now this is a constant, multiplied with a constant, it will give another constant. Let me choose that constant as b. So what will be psi 1? So psi 1 of x will be b divided by under root of k of x and then e to the power of iota integral k of x d of x. This is called first order solution. This is first order solution. And you can choose psi 2 of x equals, say, something g of psi 1 of x. But this g has to be the function of x. So this way you can proceed on. Okay? I think we'll stop here today and tomorrow we will move on from here to obtain the results. If anybody has any query, you can ask me. Come on. Okay, a very good morning to all of you. And what we have to do is we have to continue what we have done yesterday. And we have been talking about quasi-classical case, which is also known as WKB approximation. And yesterday we achieved we tried to modify the wave function. We tried to modify it. And we obtained the wave function and all the calculations that we have had, they were based on an assumption that the total energy E is greater than that of V of x, right? It was the case. Now let me, so E greater than V of x. Now, the point is that if I rewind this topic, you have a situation like this where you have classically allowed regions and you have classically forbidden regions, and you have a point. You have a point which is known as turning point, and classically what will happen to the particle, if I assume there is a particle, what will happen to the particle classically at the turning point? It will momentarily come to rest. So classically you will fail to make a connection to the region beyond these turning points, right? So what we are trying to do, what quasi-classical case is trying to do is, it's trying to generate a connection, and it tries to generate the connection in vicinity of the turning points, because at the turning points you fail. So what we do, we mathematically dissolve this problem in vicinity of the turning points, assuming a kind of slope, which we'll discuss later on. So what we have psi of x. What is it? It is, say for example, a by under root of k of x. I'll take its mod. Then you have e to the power of plus I integral k of x d of x. And then you will have plus b by under root of k of x, taking its magnitude, then e to the power of minus I integral k of x and d of x. Right? Okay? So this is your wave function for the region 2, because in the region 2 E is greater than that of V of x, right? Now if you will do the similar calculations, the calculations that we did till now in the framework of E greater than V of x, now if you will repeat the calculations for E less than k of x. So what will happen in that case? In that case, you go back to the Schrodinger's equation. What you have? You have d2 psi by dx2 plus 2m by h cross square v of x minus e. So here I can write negative, because here E is less than V of x, right? Okay? So E is less than V of x. So here you will have a psi multiplied. So you will have K. Okay? So to make my problem simple, I would like to use the magnitude of K, because this K is different from that of the K that we discussed in the previous case. So what am I trying to do is that this K will be what? It will be under root of 2m by h cross square V of x minus E. Getting my point? So when you will make all those calculations, the calculations that we made in the previous case, you will reach the same result. Your result will be psi of x is, say, C by under root of K of X, its magnitude. I'm taking its magnitude, okay? Then e to the power of minus integral K of X d of X. So this will be, say, for the region 1, and the same kind of equation you will have for the region 3, right? Because both in region 1 and region 3, E is less than V of X. So, the very first thing that you see from this solution, the solution is same. Mathematically, the solution is same. The difference is, when you talked about the region 2, you have iota. You have iota here. Okay? When you go in region 1 and 3, you lose iota. Getting my point? You lose what? Iota. Now, what is happening in region 1 and region 3? Region 1 and region 3, in this region, you have exponential decay. Right? What do you have? You have exponential decay. That's why I have taken only one term here. Right? For region 1 and region 3, your solution will be in the form of exponential decay. Getting my point? So you will not have another term for plus, e to the power of plus. Because region 1 and region 3 can be treated as something where you have exponential decay. Getting my point? So what we have now, we have two situations, we have three situations basically. We have psi 1. Now my psi 1, psi 2 and psi 3 is a different notation. It is not the notation as I gave in the previous lecture. Psi 0, psi 1, psi 2. Okay? There I had zero order solution, first order solution, second order solution. Okay? In that context, psi was meant to be like that. But here, I will choose psi 1 for the region 1, psi 2 for the region 2, psi 3 for the region 3. So what do you want mathematically? What do you want mathematically now? You want a connection. Try to understand what I'm telling you. You want a connection between the regions. And between the regions, there is a point which is not allowing you to move from region 1 to region 2, from region 2 to region 3. So what you are doing, you are tricking it mathematically. You are tricking your problem. You are tricking it in such a way that you solve these equations in vicinity of the turning points. So you are in need of what? You are in need of connection equations. Okay? You want to connect. You want to connect region 1 with region 2, region 2 with region 3. You are interested to develop the connection relation. Because only then you can have a pure quasi-classical case. And at the same time, the quasi-classical case fails at the turning points. It has no answer for the turning point. All the job that it is doing, it's doing it in vicinity of that turning point. Getting my point? So I would like to write down the equations now. Okay? So I have region 1, I have region 2, I have region 3. Then I would like to calculate psi 2, 3 and psi 1, 2. That will be a kind of target that I'll be looking for. Yes? Yes? Yeah. Oh, we'll do that later on. Okay? Yeah. Right now I'm busy. Okay, when I finish this, then you can come to me at 2 o'clock because I have another class after this. Okay? So where I was, so we have a situation like this. Okay, and now this is my psi 1, and this is my psi 2, and this is my psi 3. This is my x1, this is my x2, and what I have E greater than V of x, and this is a situation where you have x1 between, your x is ranging from x1 to x2, and then you have E less than V of x. In this case, x is, you have two regions, x is less than x1, and you have another region in which x is less than x2. Am I right? Okay? This is how you mathematically write down this. So what I need to write down the wave function. So what should I write? Let me choose psi 1 of x. Okay? So let us use a constant a by under root of k of x. And then you will have e to the power of minus integral k of x prime. I will use dx prime. Okay, no, I will not use prime here. I will use when I will connect them. Okay, so this will be equation for psi 1. What will be the equation for psi 2? It will be, say I will take a constant b by under root of k of x, and then e to the power of plus iota integral k of x d of x. Then you will have plus b1 by under root of magnitude of k of x e to the power of minus iota integral k of x d of x, and you will have psi 3 of x equal to c by under root of k of x e to the power of minus integral k of x and d of x. This is how I can write it. Now what I want a connecting relation, right? I want a connection equation. So my job is to have a connection equation. Yeah. So connection equation. So what I have, I will choose that the first one as psi 2, 3. Okay? Psi 2, 3. How can I write it? I can write it as, okay, 2 and 3. So let me use a constant. Say I have a constant. Which constants I have for 2? Which constant I have for 2? A, is it A? Come on, check it. Come on, it is B and B1. Okay? Okay, let me use that B by under root of k of x. Okay? Then you will have e to the power of, say, minus, here it is plus iota k of x prime d of x prime. Where am I moving? I am moving from x2 to x. Okay? Okay, then plus, I have b dash, is it? Isn't it? I have b dash by, is it dash or 1? b1 by under root of k of x magnitude. Then you will have what? Integral x to x1. Clear? So you are moving from x2 to x, then x to x1, e to the power of minus I integ. Come on, what am I doing? Yes. E is already there before the integral. So you will have to check. Maybe I commit a mistake. I can commit a mistake. I'm not sure about that. Okay. So then you will have kx prime and dx prime. Okay, now see where you are. You are basically in side 2. Okay, you are basically in side 2 and you want to jump into side 3. Okay, because I chose it from 2 and 3. So this is about 2. I am writing 2. Okay, so what is my target? My target is that I should reach to 3. So obviously that's why I am writing here side 2, 3. Okay, now look. Now let's go on from here. Okay. Now see now. What you have? You have a situation like this. You have a turning point, and in vicinity of turning point, you want to write your potential. But at the turning point, E is equal to what? V of x. Getting my point? Okay? And I want to write the potential in vicinity. And that potential must have a slope. Right? So what I do, I define a potential V of x. But I want to define it in vicinity of the turning point. So what I do, I say, come on, this is equal to V of x2. What is V of x2? It is the potential at x2. Are you getting it? And V of x2 is equal to what? It's equal to E. V of x2 is equal to E. So V of x is equal to V of x2 plus x2 minus x dv by dx. See, I'm moving from the turning point, which is what? V of x2. Then I'm adding another step. That step is close to the turning point. So that's why I'm writing x2 minus x and multiplying it by that small change in potential, dv by dx. Is it clear? Yes. You understand it mathematically and you can connect it geometrically. Now, V is what? Potential. What's dv by dx? With respect to distance, what's that called? So what's dv by dx? In fact, when you apply it to the gravity, it is negative gradient of the potential. You call it force. F is minus dv by dx. But I am taking only the magnitude. So for dv by dx, I will be using F. Any problem? Where F is the force. Clear? This is your potential. Okay? Yes. And you broke this potential into the two parts. Right? And you will use this potential in your original Schrödinger's equation. So what is your Schrödinger's equation for it? Yes. So it is d2. We will talk about this 3, 2, 2, 3. That's a different issue. Okay? We have already written that. So d2 psi dx2 plus 2m by h cross square. Then what you have? You have E minus V of x. But I have defined V of x. What is that? That is minus V of x2 minus x minus x2. And then you have F, you close it and multiply it by psi equal to 0. But V of x2 is equal to what? It's equal to E. You will cancel the 2. Are you getting my point? So what you have? You have a d2 psi by dx2 plus 2mf by h cross square. And then you have x minus x2 and you have a psi equal to 0. Right? So at least Yes, here it is minus. You're right. So you have at least mathematically reached to a situation where you are playing games with the turning points. And for that, you have a mathematical equation like this. Okay? So, what can you do? This 2mf by h cross square whole raised power 1 by 3 x minus x2, to take this equal to zeta. I define another variable, zeta, because I want to make my equation compact. So when you will use it, what you will get? You will get 2mf by h cross square whole raised power 3 by 2 times d2 psi by d zeta minus zeta of psi is equal to 0. Right? This is what you will obtain when you will work on it. You will obtain this equation. And obviously you will say this is not equal to 0. If this is not equal to 0, you have a differential equation like this. You have a differential equation d2 psi by d zeta 2 minus zeta psi equals 0. And this is a differential equation, and this differential equation has a solution, and that solution is called Airy solution. A-I-R-Y. Airy solutions. So again, I will not go into the Airy solutions. You can use Zetle, and there you can see the solution of this differential equation. That will be as an exercise for you. You will solve this differential equation. When you will solve this differential equation, you will obtain something important. And what is that something? I will introduce that then after this. So what I have, you remember psi 2? What was psi 2? Which I called as psi 2, 3. You have exponential, then you have another exponential. Okay. In one case you have iota, in another case you have a negative, but an exponential can be written down in terms of sines and cosines. Are you getting my point? So when you do that, what you obtain, I will introduce another constant here. What was the constant I was using there? B and B1. Here I will use B dash by under root of k of x, its magnitude. Okay, and what you will get, this times sine of integral k of x d of x prime prime plus alpha. Right? Now, the solution that I showed you, the thing that I showed you how to resolve those equations was basically to calculate this alpha, right? Because this alpha is the measure of the phase in vicinity of the turning point, not at the turning point. Not at the turning point. So when you solve those Airy equations, you will obtain this alpha, and the value of this alpha will come out to be pi by 4. What will be its value? Its value comes out to be pi by 4. You have to use a couple of boundary conditions, and finally, because you will have constants involved in those equations, when you will connect these constants, you will find that this alpha is how much? Pi by 4. And here, what was the limit of the integration? Yeah, so I should not use the prime here now. The limit was x to x1. Okay, so that I can write as x1 to x. Okay, so a negative sign might have come, that sign might have cancelled. So what you have? x1 to x. Now, symmetrically you have the other side of the potential. Okay?
Yes.
It must have the symmetrical situation. So for that I will have what? Psi 2, 1. What will be there? You will have another constant. Say d prime by under root of magnitude of k of x. Then you will have sine integral of k of x d of x. Yeah, it is from x1 to x. That will be from x to x2. Here you will have beta. Okay, so in one side I showed alpha, on the other side you show beta, but you will have the similar kind of calculations because the problem is symmetrical in nature. So for beta, what you will get? Using all those equations, for beta you will have pi by 4. Are you getting? So for beta you will have pi by 4. So I can write down here psi 3, 2 is what? It is b dash by under root of k of x. Come on. Then sine of integral of x1 to x, k of x, d of x plus alpha. And for psi 2, 1, it will be, what was that? D dash, okay? I use the d dash by under root of k of x. Then sine of integral x to x2 k of x d of x plus beta. I think you should keep the prime because finally you, okay, leave it. Don't be confused. You may be confused. Okay? These are the two connecting wave functions which we have obtained mathematically. But I calculated something at point A on the one side. I calculated symmetrically the same thing at the point B on the other side. The two must be equal. The two wave functions must be. The symmetry is demanding us that psi 3, 2 must be equal to psi 2, 1. So the symmetry is demanding that psi 3, 2 must be equal to psi 2, 1. Come on. Now what is psi 3, 2? It is b dash by under root of k of x. Then you have sine, then you have integral. Come on. x1x, then you have k of x, then you have d of x plus pi by 4. I will close it. This must be equal to what? D dash by under root of k of x, its magnitude, then sine of integral, come on, x to x2, then k of x, then d of x plus pi by 4. Right? You have a very huge, crazy equation in front of you. Right? So does it resemble something like this? P sine theta 1 equals Q sine theta 2. Right? If you have an equation like this equation can be true only when it satisfies the condition. Now what's the condition? The first thing is if theta 1 plus theta 2 is equal to n plus 1 times pi. Are you getting?
Yes.
Okay? And another condition is, because now this p is another constant, it's incorporating that by under root of k, magnitude of kx. And this p must be equal to minus 1 whole raised power n q. These are the two important conditions. Okay? Okay? So this equation can be true only if these two conditions are satisfied. So these two equations are a reality for us, for the given equation. Okay, so what will happen here? Okay, what is theta 1 and theta 2 now? Come on. So theta 1 is, so you got the rate of sine. Okay, so what is theta 1? It is integral x1 to x, then k of x, d of x, plus pi by 4, plus, integral x2, k of x, d of x, plus pi by 4 is equal to n plus 1 times pi. Right? Fine? Okay. So pi by 4 plus pi by 4 will make it pi by 2. Okay. So this integral can be stretched as integral x1 to x2, k of x, d of x, plus pi by 2, right, is equal to n plus 1 pi. Clear? Do you feel that you are reaching somewhere? Okay, can you tell me what you are reaching? Where we are heading towards? Come on. Okay, so here I can take this plus pi by 2 on the other side. So what I'll be left with, integral x1 to x2, then k of x dx is equal to n pi plus pi minus pi by 2. Am I right? Right? Fine? Yes. So this will be n pi plus pi by 2. So this will be n plus 1 by 2 into pi. Have you seen this equation somewhere in your graduate classes? You might have seen it. Come on. So this is integral x1 to x2 is k of x d of x. Right? Now, this integral, I can write this integral x1 to x2 k of x d of x as half of the loop of k of x d of x. Any problem? Okay, it's the half of the complete loop. Okay, so I can write down 1 by 2 integral k of x d of x is equal to, what was that? n plus 1 by 2 times pi. But this 2 will multiply here. So what you will get, this 2 I can multiply, this is 2 pi. Okay? Yes. So what do you have? Integral k of x d of x is equal to n plus 1 by 2, 2 pi. Come on, move on. Do you remember P? What is P? What is the relation between K and P? P is H cross K. Clear? Do you know where from this equation comes? You can do that. Okay, what's P? P is momentum. What is momentum? It is h by lambda. Okay? So if I will divide both sides by 2 pi, this will be P by 2 pi, h by 2 pi lambda. So h by 2 pi is what? That's h cross. So P by 2 pi is equal to h cross by lambda. This 2 pi will go there. What is P? P is h cross times 2 pi by lambda. But what's 2 pi by lambda? That's k. So P is what? H cross k. Clear? So that's why I wrote P is h cross k. So what's coming now? Integral is, instead of k of x, I will write P of x. Are you getting? And then you have dx. But it has divided by h cross. Huh? Because for k I have P by h cross. Right? So this is equal to what? Yeah, come on. N plus 1 by 2 into 2 pi. Now I can take this h cross on the other side. Okay? So what I'll get? I'll get integral p of x d of x is equal to n plus 1 by 2. Then you have 2 pi into h cross, but h cross is h by 2 pi. Isn't it? So I can I can cancel 2 pi and 2 pi. So what I got p of x, d of x is equal to n plus 1 by 2 h. But what is this n? It is very, very large then, because we are talking about the quasi-classical case. We are taking quantum mechanics. We are taking quantum mechanics and we are reaching to the classical regions. So n is very, very less than 1 by 2. So I can omit this 1 by 2. So I have integral p of x, d of x is equal to nh. And what is this? This is Bohr-Sommerfeld correspondence rule. This is Bohr-Sommerfeld's quantization rule. The rule that's predicted in old quantum mechanics. Right? So this way, we have reached out to the result, what's known as Bohr's quantization rule, and the things that we have left as is while discussing this topic, because it's a very cumbersome topic to be discussed in detail. So wherever we have created the shortcuts, those shortcuts are very important for you to work out. Okay, so work out in how to solve those equations, those differential equations that came across, and we obtained the value for alpha and beta. Anything else you want to tell me? Come on. Anybody? Okay, see you. Bye. Okay, a very good morning to all of you, and I welcome you all. And if I go back in our previous classes, we have started with the origin of quasi-classical case, where the basic assumptions are that you have the turning points, and at the turning points, the classical physics completely fails. So in order to connect the classically allowed region with the classically forbidden region, what we do, we exploit the potential in vicinity of the turning points, because otherwise there is no way that we can do it. So we evaluate potential in such a way that we merge the wave function, we merge the eigenfunction of one region with another region. And if you rightly remember what we did, we obtained the connection relations between classically forbidden region and classically allowed region. But the key idea was, what was the key idea? That the potential that we assume, it is varying slowly in vicinity of the turning points. And this was mathematically allowing us to get out the double derivatives in those differential equations. We could treat those double derivatives as equivalent to 0, and finally reach out to what was the final result was the Bohr quantization rule, which deliberates about the quantization of momentum or energy, whatever you say, right? So today we will be proceeding in the same direction, but now what we will have is, let us take the first case as that if you have one rigid wall problem. One rigid wall problem. So this is something that we are going to talk about, okay? So what we have the potential, but the potential is something like this. So this is my x1 and this is my x2. Now this is rigid wall. So rigid means that you have infinite potential at x1, right? So if you have infinite potential at x1, the wave function will collapse, okay? So you will have no continuity at the point of infinite potential. So rigid refers to the infinite potential. So you have infinite potential at one side, and we want to obtain the quantization rule, okay? So do you remember exactly the equation that we evaluated? What was that? What was that? Come on. Theta 1 plus theta 2 is equal to n plus 1 times pi. Okay, what was theta 1? Give me the value. What was theta 1? Come on. Yes, it was integral x to x1 k of x d of x, okay, then plus pi by 4, then plus integral, okay, this we treated it as x1 to x, then x to x2, and then k of x d of x plus pi by 4 equals n plus 1 pi. This is it. Huh? Okay. Now you will see the result for one rigid wall problem. See, you will see how softly you will obtain the quantization rule if the potential in one side is infinitely large. Now, what do you expect at x1? What is x1 and x2? These are turning points. But x1 has infinite potential. So there is no way that you can treat your potential varying at this point, because there is no chance, because you are choosing this potential as infinite potential. Are you getting? Okay? So if you have infinite potential at x1, which term you think in this equation should be equal to 0? I expect an answer from you. Yeah. Come on. What was it that was connecting the two sides? What was it in your equations? If you rightly remember, in the past, it was alpha and beta. We were treating some phase because it is the phase that will decide the connection. So, talking about x1, the phase that you calculated in your original equation, this should be equal to 0. But this part of the phase will exist. Because here, again you have what? Slowly varying potential. So this is your classically allowed region. This is your classically allowed region. And then you have classically forbidden region. And this is purely classically forbidden, because there is no chance, because the potential that you have is infinitely large. Is this clear? So I can move on now. So what I am left with, see, you have those two integrals, you merge them, what you get a closed integral. You remember? K of x d of x plus pi by 4 is n plus 1 times pi. Fine? So this pi by 4 will go on the other side. So you will have integral k of x d of x is equal to n plus 1. Let me open it. Let me remove the brackets. So this is n pi plus pi minus pi by 4. So what you will have integral k of x d of x equals n plus 3 by 4 pi. Okay? Come on. See, using quasi-classical case, even though you obtain your result, because if you treat n is very large, you can equalize 3 by 4 equal to 0. Okay? So in large limit of n, you have the result exactly as predicted, right? But the point here is, in addition to that, you can see that this 3 by 4 pi is giving us an additional information. What's that information? Yes. I think you will tell me now. So if I write here 1 by h cross integral p of x d of x is equal to n plus 3 by 4 pi. This h cross will go on the other side. So here it will have h cross. Come on. And in fact, you can write integral p of x d of x is n plus 3 by 4 pi h by 2 pi. Pi and pi will cancel, so it will be n plus 3 by 4 h by 2. What does this 3 by 4 tell us? Because 3 by 4 will come in action if n is equal to 0. So it gives us a way to understand that there is something known as 0-point energy. And you are achieving this result from quasi-classical case, WKB approximation. Is this clear to you? Okay. So this is one side of it. So you have integral p of x and d of x. Something like this. But what is p? P is the momentum. Okay. We can treat this p of x as, okay, if I cut it, if I write E equals P square by 2M. What does that mean? That means P is under root of 2ME. Right? So this closed integral you have under root of 2ME, and then you have dx is equal to n plus 3 by 4 and h by 2. Now 2 is constant, m is constant, e is constant. So this under root 2me will go out. You'll be left with integral dx equals n plus 3 by 4 h by 2. Now this d and this will cancel. Now from x1 to x2, if I assume this length is L, okay? So it started from x1, it will end at x2, right? So for x, I'll be using L. So what you are calculating here? You are calculating here under root of 2me times L equals n plus 3 by 4 h by 2. Now for large n, we can neglect the term 3 by 4. So what we'll obtain is 2me times L is nh by 2. Are you getting? Yeah? So I can do scaling on the both sides. So what will be left with 2me is equal to n square h square by 4l square. Right?
Yes, sir.
So I can calculate E now. Okay, you have the quantized energy levels. So E is n square h square by 4m L square. Right? Okay? Now we have another case. What is that? Now would like to treat a problem in which both the walls are rigid walls. Now what is that problem? That's a problem of particle in a box. That's a problem in which you treat a constant potential, okay? You assume that inside the box the potential is what? Potential is zero, okay? Potential is zero. You treat it that way. So I can use my results to obtain the result for particle in a box situation. But what is that particle in a box situation in our case? What's that? That's what you have now. You have your potential is something like this. There is everything is here and everything is here, but your potential is zero. So you have x1 and you have x2. x1 and x2 are what? They are turning points. They are strong turning points. They are the points where you cannot exploit a slowly varying potential. And this will verify the fact that the beginning of this problem, the beginning of this quasi-classical case, based on some assumptions, is a right theory. Because we are able to obtain the results of which are purely quantum mechanical in nature, talking about particle in a box, in which you have two rigid walls. Okay? You have two rigid walls. So you have two rigid wall problem now. Now it must be extremely simple for you to solve it. Okay? Again, tell me about the equation. What was that? Theta 1 integral, yeah, x1 to x, k of x, d of x, plus pi by 4, plus integral x to x2, k of x, d of x, plus pi by 4 is equal to n plus 1 times pi. Now in your case, you have two rigid walls. So there is no communication between this wall and what is outside that wall. There is no communication between this wall because you are treating potential to be infinite. So treating potential to be infinite means you will have no connection at this point. You cannot develop a connection relation. So there should not exist the phase pi by 4 on one side. There should not exist the phase pi by 4 on the other side. So both the things should be equal to 0. Is this clear? Clear? Okay. So what we are left with? We are left with integral x1 to x, k of x, d of x, plus integral x to x2, k of x, d of x is equal to n plus 1 times pi. So again, for large n. So 1 can be neglected. So what this becomes? This becomes integral k of x, d of x equals n pi. Right? Now what is k? You have p equals h cross k. So what is k? So k is p by h cross. So I can use for k of x here p of x by h cross. So what you will have? You will have integral p of x d of x is equal to n pi h cross. Is this clear? Right? Yes, sir. Now for p of x I will use under root of 2me because the potential, you remember the problem of one-dimensional box? Yes. The potential between the walls is 0. It doesn't have any potential energy. It only has kinetic energy. So under root of 2me d of x is n pi h cross. So under root 2me will be out. You will have integral of dx leading us to n pi h cross. So you can see this integral and differential will cancel because your limit will move from 0 to L. Okay? From x1 to x2 you have a length equal to L. So what you will get here? You will get here L. So you will have under root of 2me, then you will have L. Okay, this is equal to n pi h cross. As usual, I will go for scattering on both sides. What I will have 2m e L square is equal to n square pi square h cross square. Right? So I can calculate the energy. E is what? N square pi square h cross square by 2ml square. This is the result of your particle in a one-dimensional box, isn't it? And you can use for h cross equal to h by 2 pi also. That's another way of writing it. So you can see that we have seen the two important cases that are the basis of the modern quantum mechanics. They seem to be the approximation of the quasi-classical case, right? And we have resolved both the problems. Problem one was about treating quasi-classical case in which one wall is a rigid wall, okay? And in the second problem, what we did, we treated both the walls as rigid walls. And the results are completely agreeable, and these are the real results that we understand by actually solving the problem of a particle in a box. When you solve Schrodinger's equation, you obtain the quantization of energy for the particle in that box. And what does it tell us? It tells us a story, a very beautiful story. It tells us that the particle in a box cannot have all possible energies. Can we imagine that in this room? If I have a ball and if I shoot this ball, can you imagine that this ball will have quantized energy? Classically, no. Classically, it will have at all points the ball will carry the energy. But in a one-dimensional quantum mechanical box, the particle cannot have all plausible energies because your energy is dependent on n. And where from we got this n? We got it from using the boundary conditions, right? And n is what? It is an integral number. N is not something like 1, 1.1, 1.111. No. N is either 1 or 2 or 3 or 4. So that means the particle that we have, it will have energies in the box, but these energies will be quantized energy. It will have only some defined energies in the box. It will not have all possible energies. That's what differentiates a quantum mechanical description from the classical description. Right? Any questions? Do you have any questions? You can ask me. Okay, so with this, I would like to stop here. We will move on from here. Stop it.